Some people argue that since there's been hundreds of millions of years available, the probability that there's the chance that these things could happen in hundreds of millions of years. But that's not true. Time actually can be an enemy when it comes to organic synthesis. Prebiotic synthesis is before biology. So one has to make chemicals. Many of the chemicals that need to be made for life are kinetic products, meaning that they're not the most thermodynamically stable form. For example, carbohydrates, which is the main class of compounds. These are the units that hook together DNA. These are the units that have identifying aspects on cell structure. These are the units that the cell is going to need for the energy of life. Carbohydrates are kinetic products, meaning that if they should form, they would decompose. They decompose over time. In relatively short amounts of time, they decompose. The very reactions that make them, unless somebody is there to pull them out, to fish them out, to stop the process and to put them in a bottle under inert conditions in a freezer, and not just one, there's many, many different types you have to do this, they end up going through a process of what's referred to as caramelization, meaning that they polymerize. They polymerize. The very aldol reactions that were used to make them just continue. And you get polyaldols, you get polycondensation reactions, and they caramelize. Or they undergo, with formaldehyde, which is a presumed prebiotic chemical, they undergo rapid Cannizzaro reactions. So the aldehyde is oxidized to formic acid, and this nice carbohydrate that you made has just been reduced. So the aldehyde from the carbohydrate has gone back to an alcohol. So there's competing reactions. So time does not solve the issue. The other problem is if you had 400 million years to get to a certain point in a synthesis of a particular class of compounds, now you run out of material. Anytime you do synthesis, you run out of material, even when you've optimized the yields, and you got to go back to the beginning. Well, say it took you 400 million years to get to a certain point on a synthesis. Now you have to go back and make more. But how do you go back and make more? Because nature never kept a laboratory notebook. Doesn't know how to go back. Never kept a record. So even if it could make more, it doesn't know how to, so it's got to start all over again somehow. But it doesn't know how to start over again. Doesn't know why to start over again because it doesn't know what it's going toward. So if you look at it, people have been trying for a long time. If we just take Miller-Urey as the first example, where Miller and Urey took some basic chemicals that are presumed on a prebiotic earth, hydrogen cyanide, formaldehyde, and CO2, and they put those across a high voltage, simulating lightning, you can get some racemic amino acids out of those. But those racemic amino acids were racemic. Okay, that was in 1952. That was 2/3 of a century ago. What's happened in 2/3 of a century since Miller-Urey in other fields? Well, we've had human space flight. We have satellite connectivity. We have the internet. We have the entire silicon era of microchips, and we have computer technology. We have all of this. In the same 66 years, 2/3 of a century, we are still exactly where Miller and Urey were. We make a barrage of stereo-scrambled chemicals, nowhere close to even knowing how to make them and hook them together. They got to get hooked together in the proper order. We are clueless on this, clueless, because time doesn't solve this. Even with all our ingenuity, time is not going to solve the problem. You let these chemicals that have been made, you let them sit around, even for months, and you can look even in the origin of life researchers themselves. When they've let these go for weeks, they show the degradation of these in a period of weeks. Weeks is the twinkling of an eye when it comes to prebiotic timescales. The chemicals decompose. The environment for the chemicals, environment rich in ammonia, is going to turn carbonyls into imines. This is going to cause further destruction. The ammonia environment itself is quite basic. You're going to have extended aldol reactions coming on. So to think that the molecules could be made and sit there waiting for other molecules to come in. It doesn't happen. Organic chemistry doesn't work that way. Any student that is lazy enough to set up reactions and like to go home for the weekend without working them up pays the price for that, with a depressed yield generally. As soon as the reactions are done, or as soon as what you want is the optimized yield, you have to stop that reaction, get it away from the starting materials, or else what happens is it goes on to polymerized product. Especially when you're making kinetic products, which is not the thermodynamically most stable product, which is exactly what you get in many of the chemicals that are needed for life. So time is actually the enemy